arresting momentum, chain drags, and wooden masks. Okay, let's jump right into this explainer. Stopping a massive ship that was literally just stationary a moment ago is one of the most viscerally dramatic, heart-pounding engineering operations in shipbuilding. We're looking at the traditional end launch today, specifically diving into the raw mechanics of how engineers arrest 10,000 tons of momentum using nothing but chain drags and wooden masks. Let's get into it.
So how exactly do you stop 10,000 tons of steel moving at 10 kilometers per hour? To put that into perspective, that's hitting the water at about 3 to 5 meters per second. Once the mechanical triggers on the slipway are finally released, gravity completely takes over. It pulls this colossal weight down tracks that are slicked up with layers of special grease. And man, it's an awe-inspiring sight, but it immediately creates a sort of narrative vacuum of impending disaster. Why? Well, because the harbor basin this ship is sliding into is usually pretty restricted in size. If we can't arrest that incredible momentum within a really short, highly specific distance, that massive hull is absolutely going to crash right into the opposite bank of the harbor.
Clouds of dust, spray, and raw controlled chaos. That really is the reality of the traditional launch. Stopping a vessel of that massive scale is honestly as raw as engineering gets. You see, there are no delicate electronic brakes here, no reverse thrusters to bail you out. We are relying purely on friction, gravity, and some incredibly heavy metal to get the job done. It's this spectacular, high-stakes clash between the kinetic energy of the ship and the physical resistance we can put in its way.
Enter the primary hero of our story. Chain drags. These are massive lengths of anchor chain, where each individual link can weigh hundreds of kilograms. They're attached to the sides of the ship's hull using these heavy wire drag lines, and then laid out across the harbor floor. Now, what's really fascinating is that these chains don't just act as a static deadweight dragging the ship backward right from the start. Instead, they're carefully laid out, often in a horseshoe pattern, creating a highly calculated dynamic braking system that actually adapts to the ship's speed.
Step 1, the chains lie flat, providing zero resistance. Step 2, the ship accelerates, lifting the chains sequentially. And Step 3, each lifted link adds progressive drag force. Let's unpack how that dynamic braking actually builds. When the ship first starts sliding down the ways, those chains are just lying flat on the ground. Initially, they give zero resistance, and that's absolutely crucial because you need the ship to build enough momentum to actually slide off the slipway in the first place. Then, as it accelerates and hits the water, those wire lines pull taut, and the chains are lifted off the harbor floor one by one. Here's the engineering magic. Each newly lifted link adds a progressive drag force. This sequential lifting guarantees a smooth, controlled deceleration, rather than a violent, jerky halt that could easily snap cables or damage the ship.
Chain drag force equals mass per meter of lifted chain times gravity times the sine of the launch angle. Now, absolutely none of this is left to guesswork. Naval architects have to calculate the exact kinetic energy of the ship at the precise moment it enters the water. And once they have that number, they have to size the total mass of the chains to perfectly absorb all of that energy within the available stopping distance of the harbor. On the left, undersized chains mean the ship hits the far bank. On the right, oversized chains mean the ship stops dead, risking structural failure. This comparison brilliantly illustrates the extreme high stakes of this math. If the engineers miscalculate and undersize the chains, the ship just won't slow down fast enough, and thousands of tons of fresh steel will plow directly into the far bank. But if they oversize the chains, the resistance hits too strong, too fast. The ship stops dead in the water, and that sudden violent deceleration creates incredible structural loads that literally risk ripping the hull apart. There is absolutely zero margin for error here. The calculation has to be spot on.
The tipping moment, a severe pivot on the forward poppets. You see, stopping the forward motion isn't the only danger. There's another critical phase called the tipping moment. As the stern of the ship enters the water, buoyancy kicks in and starts lifting the back end up. Meanwhile, the bow is still resting up on the slipway, on these temporary timber and steel supports called forward poppets. So the entire ship effectively becomes a giant seesaw. If buoyancy lifts that stern too sharply before enough of the hull is actually in the water, the ship can pivot forward dangerously. And if that pivot is severe enough, there's a real threat of dropping the heavy steel bow completely off the ways and smashing it directly onto the harbor bottom,
Converting a potential structural failure into a minor incident requiring timber replacement. So, how do we prevent the bow from being crushed if it does tip too far? Well, engineers use a brilliantly humble savior known as a wooden launching mask. Basically, this is a protective timber framework built right against the bow of the ship. If the hull tips severely and the bow drops toward the concrete or rock of the harbor floor, this wooden mask makes contact first. Instead of the steel hull taking a catastrophic point load, the timber absorbs the impact by collapsing progressively.
It's an elegant, sacrificial layer of protection that turns a massive structural disaster into a quick woodworking fix.
Modern launch alternatives include dry dock float-offs, providing zero dynamic loads, side launches for narrow rivers, and hydraulic ship lifts. As awe-inspiring as these traditional end launches are, the shipbuilding industry is naturally moving on. Modern shipyards are increasingly turning to safer, highly controlled alternatives. For instance, you've got dry dock float-offs, where the ship is built in a basin and the water just gently rises to meet the stationary hull. Zero dynamic loads, no sliding, no chain drags, no drama. We also see side launches designed for narrow rivers, where the ship just rolls broadside into the water. And then there are hydraulic ship lifts, which are essentially massive synchronized elevators, lowering the entire ship into the water with absolute precision.
As shipbuilding evolves toward calm, zero-impact float-offs, what ingenious feats of raw mechanical problem-solving might we be leaving behind in the dust and spray? These modern methods are for sure safer, more efficient, and way easier on the ship's structure. But it kind of leaves you wondering, doesn't it? We're trading this awesome, controlled chaos for quiet precision. It's absolutely a necessary evolution for heavy engineering, but until those traditional slipways are completely gone, I really hope you walk away from this explainer with a profound appreciation for the brilliant, thundering mechanics of the chain drag and the humble wooden mast. Thanks so much for joining me, and I'll catch you on the next one.